Hello, this is Dr. Hanaa Assil, and today we're talking about reaction kinetics. This is for the IAS chemistry. Remember that we said kinetics, first of all, means rates of reaction, actually. So the rates of reaction depend on the collisions. We said there was a collision theory that says particles that collide with a very small amount of energy will not react. So we call that an ineffective collision. But if the particles collide with a certain amount of energy, which we call activation energy, or more than activation energy, then they have enough energy to collide and react, and that is called an effective collision. So what are the factors that would increase the rate of a certain reaction? Remember that the first thing I can do to increase the rate of a reaction is increase its temperature. This is because when we increase temperature, particles will gain more kinetic energy, move faster, collide faster, and more of the molecules will have energy higher than the activation energy. Remember that activation energy is the minimum amount of energy needed to start a reaction. So if the particles have energy higher than the activation energy, then they will collide and form a reaction faster than if they have lower energy. So remember that when we increase the temperature, this causes the particles to gain more kinetic energy. And remember that we never say gain more kinetic energy unless if we're talking about increasing temperature. Usually you're required to draw a graph. So let us say I do the experiment at 25 degrees Celsius. If I do it at a higher temperature, then the graph will be steeper and will end at the same final volume of gas if we're using the same amount of reactant. Pressure, we said pressure applies only if we're talking about gases. You know that gases, the particles initially are far apart. So if I increase pressure of a gas, this increases the rate because basically increasing the pressure means pushing the particles closer to each other. So more collisions are likely at the same time. Surface area, we said if I have a big piece of, let's say, magnesium, a lump of magnesium, only the particles on the surface are reacting. But if I cut this big piece into tiny little pieces or I crush it into a powder, we say this now has larger surface area. So if they are smaller size of particles, it is larger surface area, so more particles collide at the same time. Increasing concentration means I add more of the reactant particles. So if we say that we're repeating the experiment with concentrated acid, that means I have more particles colliding at the same time, and that increases the rate of the reaction. Catalyst, we said a catalyst is a substance that increases the rate of a reaction without being used up. And in O level, we said, why does this happen? Because it provides an alternative pathway for the reaction, which lowers the activation energy. So remember that a catalyst speeds up the reaction because it lowers the activation energy. Catalysts are very important in industry because this makes the processes more sustainable. Because when I use a catalyst, then I don't need to heat the reaction up to a very high temperature. So we're using less energy, and that means it is more economical to use a catalyst than heat the reaction to a high temperature. Again, remember that when we add a catalyst, it speeds up the reaction. How does it speed up the reaction? By lowering the activation energy. Remember that we said the activation energy is the difference in energy from the reactants to the top. That top is where you have the energy of the intermediate. So with an uncatalyzed reaction, the energy of activation is very high. With a catalyzed reaction, it lowers the activation energy, and that means there will be more particles that can collide and react because they will have enough energy to do that. So for an exothermic reaction or for an endothermic reaction, the catalyst lowers the activation energy. So how do we study the rate of a reaction? That depends on which reaction we're talking about. We said if the reaction is something that gives out a gas, then I can do the reaction in a flask, conical flask connected to a gas syringe, and I measure what? I measure the volume of gas per minute or per a certain time, unit time. We said for any reaction, if I'm measuring the volume of a gas, at the beginning, the reaction is very fast because I have a lot of particles of the reactants colliding. So the increase in the volume of gas is very fast. But then towards the end of the reaction, the particles of the reactants have been used up. So the rate slows down and it becomes zero at the end so that no more gas is given off, and that's when the reaction has finished because all the reactants have been used up, so there is less particles colliding. If we have this kind of graph, we said if we do an experiment and it gives graph A, remember that graph number 1 is a slower reaction, graph number 2 is a faster reaction, but all of them end up at the same volume of gas. That means they all started with the same amount of reactants. Now graph 3 is faster and it has more volume of gas given off. This means that we started with more amount of reactants. What if we want to measure the rate but without a gas syringe? I can do that by putting the flask on a balance, and what we're measuring here is the change in mass per minute. So as the gas goes out or escapes from the reaction, then the mass will decrease until all the reaction has finished and there will be no more decrease in mass. So this is another method of measuring the rate when a gas is being given off. But what if there is no gas given off? We said if a precipitate is formed, then what we do is we put the flask on an X and we look through the solution and measure the time taken for the X to disappear. So as the solution becomes cloudy, then the X will disappear. A faster reaction will take less time for the X to disappear. Now, the new part in the AS is the Maxwell-Boltzmann distribution. So we said if we draw a graph of number of molecules with a certain energy versus the energy of each of these molecules, we will find that the graph will look as shown. Most of the particles have intermediate energy. A few of them will have less than the intermediate energy, a few of them will have more than the intermediate energy. Notice that the activation energy is somewhere on the graph, and only the particles that have energy higher than the activation energy, that's the shaded part that you have down there, these are the only particles that will actually collide and react. All the other particles with less energy will just bump into each other, collide with each other, but there will be no reaction. There will be ineffective collisions. So what happens if we increase temperature? Why is it that when we increase the temperature, the rate of the reaction is faster? This is because if I have the reaction at T1, and then I increase it to temperature T2. Now, what happens to all the particles? If you increase the temperature, we said the particles gain more kinetic energy. Notice that the activation energy does not change if I'm increasing temperature, but the shape of the graph changes so that now more particles have energy higher than the energy of activation, so more of these particles will have effective collisions. So please notice the shape of the curve. As we increase temperature, the curve moves more to the right and with a lower uh, maximum part of the graph. So T2 is higher than T1. Now the particles, more particles have energy higher than the energy of activation. But again, the energy of activation does not, in itself, does not change. But what if I add a catalyst? We said, how does a catalyst speed up the reaction? First of all, we're not changing the energy of the particles themselves, but we are lowering the activation energy. So the activation energy of the reaction with a catalyst is lower, and that means more of the particles will have energy higher than the activation energy. So notice that when we use the catalyst, it is the position of the activation energy that moves to the left, so that now a bigger area is after the energy of activation, so more particles have energy higher than the activation. Now, what does a catalyst do actually? How does the catalyst act in order to lower the activation energy? In some catalysts, in most of the catalysts, the surface of the catalyst attracts the particles of the reactants, so that the particles of the reactants tend to be absorbed on the surface of the catalyst. This brings the particles nearer to each other. It weakens the bonds in the reactant, so the reaction tends to happen faster, and the products can then separate from the surface of the catalyst. So we're doing some practice questions very quickly. This is the first one. Magnesium metal reacts with hydrochloric acid. Which change in condition would have no effect on the initial rate of the reaction? So the first option here you have is an increase in the volume of the acid. Remember that this would not have an effect on the initial rate of the reaction. But if we decrease temperature, yes, it will lower the rate. Increase the surface area will increase the rate. Decreasing concentration will decrease the rate. Then he says the diagram shows the general shape of a Maxwell-Boltzmann distribution curve for the particles present in a reaction mixture. Now, how does the peak change when the temperature of the reaction is decreased? So that means that he's saying that this graph that he drew is at the higher temperature. So if I were to draw the graph at the lower temperature, what would happen to the peak? Will it be shifted to the left or to the right? Remember that. If this is the higher one, then the lower one is shifted to the left and with a higher peak. So it should be shifted to the left with a higher peak. The activation energy of an uncatalyzed reaction is represented by the vertical line EA on the horizontal axis. The shaded areas are the areas under the curve. How do the two shaded areas change if when a catalyst is added, if at all, when a catalyst is added? Remember that which one is area A and which one is area B. Area A is the one before the energy of activation. Area B is the one after the energy of activation. So what he's saying is he is going to use a catalyst. So what happens is that we said the energy of activation will move to the back, will move to the left. So the area A will decrease and the area B will increase. And we said that's why we have more particles now having energy higher than the energy of activation. Again, this question says the Maxwell-Boltzmann diagram shows the distribution of molecular energies for the gaseous system with the activation energy labeled with and without a catalyst, the area indicating the number of molecules with energy exceeding the activation energy in the presence of a catalyst. Now, where is EA with the presence of a catalyst? That's that longer line. So the number of molecules with energy higher than the activation energy would be whatever is after it to the right. So that is Y plus Z. All of these particles will have energy higher than the activation energy. Now he's saying when the temperature is increased, the peak in the Maxwell-Boltzmann What happens to the peak of the graph when the temperature is increased? Remember that we said it will move to the right and the height will decrease. This question is about Maxwell-Boltzmann energy distribution, the diagram for an increase in temperature from T1 to T2. Again, which of these is for T1 to T2? Look at option B. We said if we're increasing, that means T2 is more than T1, then it moves to the right and with a lower peak. The rate of reaction between calcium carbonate and acid increases when we do what? Okay, so we want the rate to increase. The particle size decreases. Yes, that would be correct. We said if the particle size decreases, that means you have powdered, for example, instead of lumps, that would increase the rate. Now, option B says 1 mole is used instead, 1 mole of nitric is used instead of 1 mole of hydrochloric. That's the same concentration. 0.5 and actually yes, it will be the same concentration. 0.5 mole per decimeter cube sulfuric is used instead of 1 mole. Remember that the difference between sulfuric and hydrochloric and nitric is sulfuric has 2 replaceable hydrogens. Hydrochloric and nitric have 1 replaceable hydrogen. So if you're using half of the sulfuric acid instead of 1 mole of HCl, well, that would be actually the same. And if the pressure is increased, well, we cannot say pressure increased because we're not talking about gases. The next question says hydrogen peroxide decomposes forming water and oxygen. Which change does not increase the reaction rate? Adding does not increase. Please note whether he wants the yes or the no, or the correct or the not correct. So here he's asking which change does not increase the reaction rate. Adding powdered catalyst, no, that would increase. Increasing the concentration, no, that would increase the rate. Increasing the pressure, well, we're not talking here about gases, so we cannot increase pressure to increase the rate. Okay, consider the following reaction. Increasing the pressure increases the reaction rate because it, well, which of these? We said if I increase the pressure, first of all of these are gases. And we said when we increase the pressure in a gas, the reaction rate increases because what? Because you have particles nearer to each other, so there are more collisions happening at the same time. So it increases the collision frequency. Remember, you cannot say it increases energies if you're not increasing temperature. The only time that the particles gain more energy is if we're increasing temperature. A Maxwell-Boltzmann curve shows the distribution of molecular energies when the temperature in the system is increased. Again, when the temperature is increased, what happens? We said it will lower the peak and move it further to the right. Okay, again, which graph correctly shows the Maxwell-Boltzmann energy distribution curve? Remember that the energy distribution curve is as he draws it in A. This is how we draw the Maxwell-Boltzmann energy distribution for a normal reaction. Then he says the curves in D2 and D3 show a distribution of molecular energies at a temperature T1. Label the axes. First of all, how do we label the axes? There are number of molecules versus energy. Now, on the diagram below, draw a curve to show the distribution of molecular energies at higher temp. Again, what would the curve look like at a higher temperature? It will look like something like this. We said the peak will be lower and the graph will shift to the right. Use your diagram with further labelings as necessary to explain why the rate of a chemical reaction increases when the temperature is increased. We said at higher temperature, more molecules have energy greater than activation energy, so there will be more effective collisions. Remember, when we increase the temperature, the energy of activation is at a certain point. It does not change. It is the shape of the graph that changes when we increase the temperature. Use the diagram below with further labeling as necessary, so we label the axis, to explain why the rate of a chemical reaction increases when a catalyst is active. Remember that if I have a catalyst, the shape of the curve does not change. What happens is the energy of activation with no catalyst will move to the left so that it becomes energy of activation with catalyst, and more particles have energy higher than activation energy, so there will be more effective collisions. Please remember all of this. The only two conditions we have are increasing temperature and increasing catalyst. If we increase temperature, the curve shifts to the right and the peak is lower. If we increase if we add catalyst, the energy of activation moves to the left, so more particles have energy higher than activation energy. Again, which of these is the diagram for Maxwell-Boltzmann? Remember, it is diagram A, not any of these other ones. The rate of the reaction between sodium thiosulfate solution and dilute hydrochloric acid increases as the concentration of sodium thiosulfate increases. Which of these occurs when the concentration of the solution increases? So he's increasing the concentration. What would happen to the activation energy? Nothing. Remember, the activation energy changes only if I add catalyst. Changing concentration will do nothing to the activation energy, but you will have more collisions at the same time, so collide more frequently because now you have more particles in the solution. Consider the following exothermic reaction. If the mass of A and volume and concentration of the solution of B are constant, which of these changes in conditions would result in faster rate? So which of these would increase the rate? Now, the size of the particles, should it be doubled or halved? If I want the rate faster, well, it should be halved. We need smaller sizes for faster reaction. What happens to the temperature? Well, it should be increased. Higher temperature would increase the rate. These questions concern Maxwell-Boltzmann distribution. What is the best way to describe the activation energy of a reaction? Remember, if we say what is meant by activation energy, it is the minimum energy required for a reaction to occur. How does the curve above change when the temperature is increased? Again, when we increase temperature, what happens to the curve? The peak decreases and the curve moves to the right. Okay, a lump of malachite reacts with 40 centimeter cubed of 0.5 mole per decimeter cubed hydrochloric acid. The rate of the reaction can be increased by which of these? Well, let's look at the options. Increasing pressure, that doesn't apply. We're not talking about gases. Crushing, yes, crushing the malachite into powder would increase the rate. The other options say replacing the acid with 80 centimeter cubed of 0.25. Actually, if you look at it, you know that the number of moles is concentration times volume. So actually, this would be the same number of moles in both cases. So it would not increase the rate, and using a magnetic stirrer would not. Consider the following reaction carried out with 0.1 gram of magnesium ribbon and excess hydrochloric acid. Which method should be used to follow the rate? Well, this is something that's giving out hydrogen gas, so I should measure the volume of gas using a gas syringe. Which of the lines shows the effect of adding a catalyst? Remember that we have graph X. Now, if I add a catalyst, which graph will I get? Graph B, because that is the one that is faster, steeper, slope, and ends at the same concentration of product, since he did not mention that he was using more of the reactants. Now, a Maxwell-Boltzmann distribution graph can be used to illustrate the effect of increasing temperature. Again, which area on the graph below indicates the increase in number of molecules that have enough energy to react? Again, when we increase the temperature, which part has molecules that will react? It is area C will be added to area D, so he's talking about which one will increase the number of molecules. Originally we had D, so the area that will increase the number of molecules is C. Draw a Maxwell-Boltzmann diagram labeling the activation energy and the vertical axis. Well, the vertical axis, remember, it is the number of molecules. The activation energy is the amount of energy after which any particles will react. So it is usually in that part of the graph. Now use your diagram to explain how the presence of a catalyst affects the rate. Remember, we said the catalyst moves the energy of activation to the left. So it provides an alternative pathway with lower activation energy. So now more molecules have energy higher than the activation energy, so there will be more effective collisions. So just how solid catalysts work, remember we said the reactants are adsorbed on the surface of the catalyst. This weakens the bonds, so the reaction is faster. Products separate from the surface of the catalyst. Consider this Maxwell distribution, Maxwell-Boltzmann distribution curve. The shaded area of the diagram indicates the total number of particles that what? He's shading the part before the energy of activation. So these are the number of particles that do not have enough energy to react. Okay? Which of the following will not affect the rate? So which one does not affect the rate of this reaction? Pressure, because we're not talking about gases. The diagram below shows Maxwell-Boltzmann. If the temperature is lower, what would be the effect? Again, if we lower the temperature, then the graph will move to the left and it will be higher. Which of the following would shift the activation energy? Remember that removal of the catalyst would be the one that would affect the position of the activation energy. The rate of the reaction between powdered magnesium carbonate and dilute hydrochloric acid was monitored. State two factors that would decrease the rate. Now he's having what? Powdered magnesium carbonate and dilute hydrochloric acid. So the two factors that would decrease the rate is if I use lumps instead of powder, since the lumps would have smaller surface area, so less particles collide at the same time. Another would be use more dilute acid, since there will be less particles, so less collisions at the same time. Then he says, suggest why pressure has little or no effect on the rate of this reaction. Of course, this is because pressure will only affect gaseous reactants. So that's the end of this. Please make sure you study all of this very well, and I hope it will be helpful. Thank you.